In this video, we are going to discuss about the polarity of bonds and fajangs rule. Now, we know that a chemical bond, they are mainly of two types, ionic bond and covalent bond. Now, it is found that there is no bond which is 100% ionic or 100% covalent, which means that even a covalent bond possesses or it has some ionic character, and an ionic bond possesses some covalent character. So in this video we are going to see how a covalent bond gets some ionic character and how an ionic bond gets some covalent character. First, let us discuss how a covalent bond gets some ionic character. We know that covalent bond, it's formed by the sharing of electrons, and we have no charge in covalent bond. Now, we are going to see how this covalently bonded molecule is going to get some charge, which means it possesses that ionic character also. Okay, so before we see that, we have to see a classification of covalent bond. One classification is non-polar covalent bond. So let's see the classification of covalent bond. First is non-polar covalent bond. Now, what do you mean by non-polar covalent bond? When covalent bond is formed between two similar atoms, the shared pair of electron is equally attracted by two atoms. So the electron pair is situated exactly between the two identical nuclei, and this bond is called non-polar covalent bond. So non-polar covalent bond is formed by two similar atoms. For example, H2 molecule. This is a non-polar covalent bond, and we know H2 molecule means we have one bond, which means two electrons, and since this is a non-polar covalent bond, since these are two similar atoms, this bond pair of electron is equally attracted by both the atoms, which means where will be the position of this electron? It will be exactly between the two nuclei of hydrogen atoms. Okay, so this is non-polar covalent bond which is formed between two similar atoms. Another example for non-polar covalent bond is chlorine molecule, another example is fluorine molecule, etc. Okay, so in this type of molecules, it's difficult to find some ionic character. So we have a second type of covalent bond which is called polar covalent compounds. So second type, first type is non-polar covalent bond, second type is polar covalent bond. Now, in this polar covalent bond, the shared electron pair, that is the bond pair, will displace more towards the electronegative atom. As a result, the electronegative atom gets a partial negative charge and electropositive atom or the other atom gets a partial positive charge, and this is called a polar covalent compound. So, polar covalent compound is formed by dissimilar atoms in which the bonded electron pair is displaced more toward the electronegative atom. For example, hydrogen fluoride, HF. Hydrogen fluoride, this is the bonded electron pair. Now, this is a polar covalent bond because this bond electron will be shifted more towards the electronegative atom, and you know fluorine is the most electronegative element in the periodic table. So, the bond electron will be more closer towards fluorine atom. As a result, what this fluorine gets? It gets a partial negative charge. Partial negative charge denoted as delta minus, and hydrogen gets a partial positive charge. Positive means that partial, it is partial, a small positive charge, and a small negative charge, because that electron is moving away from hydrogen towards fluorine. So we can say that this is an example for what? Polar covalent bond. Here ionic character, this covalent molecule possesses some partial ionic character. And how is that partial ionic character observed in this? By the displacement of the bonded electron pair towards highly electronegative atom. Now another example for polar covalent bond is HCl, hydrogen chloride. Chlorine is more electronegative, so the bonded electron will be more towards chlorine. As a result, chlorine gets partial negative charge and hydrogen gets partial positive charge. Okay, now we say that this molecule is polar in nature, or it is polarized, or we can say as a result of polarization, this molecule possesses dipole moment. Okay, so polar molecules possess dipole moment. This is something very important. Polar molecules possess dipole moment. And dipole moment is denoted by mu. Okay, now let's see the definition of a dipole moment. Dipole moment is the product of magnitude of charge and the distance between the center of positive and negative charge. It is the product of magnitude of charge. For example, you take two atoms A and B. Now, this is the distance D, and this is plus Q and minus Q. Q represents charge. So the definition of dipole moment, mu, is it is the product of magnitude of charge. Charge means it can be either positive or negative, and so it will be Q into and the distance between the center of positive and negative charges. So this is the expression for dipole moment, product of magnitude of charge and distance between the center of positive and negative charge. And the unit of dipole moment, is d by and denoted by capital D. Okay, so this is the unit of dipole moment. So polar molecules will possess dipole moment. Okay, now let's see some notes related to this polarity and dipole moment. Greater the electronegativity difference between the bonded atoms, greater is the dipole moment value. For example, if you take hydrogen fluoride, HF, you know that fluorine is highly electronegative and hydrogen is less electronegative. So there is a large difference in electronegativity between these two atoms. So greater the electronegativity difference between the bonded atoms, greater is the dipole moment. Now the next note is dipole moment is a vector quantity. Vector quantity, which means it has both magnitude and direction. Vector quantity. And how will you represent a dipole moment? It is represented by an arrow with tail on positive side and arrowhead pointing towards the negative atom. For example, HF, we know that HF is a polar molecule. HF is a polar molecule. How will you show or how will you represent the dipole moment in HF? Fluorine is highly electronegative, so it's represented with an arrow with the arrowhead pointing towards more electronegative atom and a tail on the less electronegative atom. Okay. Now, next note is in polyatomic molecules. Polyatomic molecules means molecules which contain 3 or more than 3 atoms. In polyatomic molecules, the net dipole moment is the vector sum of dipole moment of all bond dipole. So, if it's a polyatomic molecule, the net dipole moment is the vector sum of dipole moment of all bond dipole. What do you mean by bond dipole? If it's a polyatomic molecule, there will be many number of bonds. So each bond will have a value for dipole moment. Okay, that is called bond dipole. Bond dipole means the dipole moment due to individual bonds. So what's the meaning of the word bond dipole? Dipole moment due to individual bond. So if you are asked to find the dipole moment of the molecule, polyatomic molecule, it will be the vector sum of dipole moment of all bond dipoles. Means we have to add the dipole moment value of each bond to get the dipole moment of that polyatomic molecule. Okay, so these are the notes. Now let's see examples for this dipole moment. Example 1 is water molecule. Now H2O, you can see the atoms are hydrogen and oxygen, and it's a polyatomic molecule, and there is a large electronegativity difference between hydrogen and oxygen, and you know that oxygen is highly electronegative in nature. So this is a polar molecule because that bond electron will be shifted more towards oxygen. As a result, oxygen gets a partial negative charge and the hydrogen atoms gets a partial positive charge. Now we are going to show the dipole moment in water molecule. So since this is a polar molecule, it possesses some dipole moment value. Now the shape of water molecule is bent shape, H2O, like this. Okay, now you can see oxygen is more electronegative. And how will you show the dipole moment? These are the two bonds. There are two OH bonds in water. Two OH bonds. Now the dipole moment for this OH bond is in this direction, because we know how we represent the dipole moment with an arrow, with the head pointing towards the electronegative atom and the tail on the positive center. So this is the bond dipole due to one OH bond, and this next OH bond also will be in the same direction. Okay, now this is the second bond dipole due to second OH bond. Now you can see it's a polyatomic molecule, so the net dipole moment will be the vector sum of dipole moment of bond dipoles, each bond dipole. So you can see this and this, since both are in same direction, the net dipole moment value will also be in the same direction. So the water molecule, the dipole moment value is 1.85 d by, or capital D. Okay, so this is the first example. Now the second example is carbon dioxide molecule. Now this is a very important question. Carbon dioxide molecule has zero dipole moment value, means its mu value is equal to 0. What is the reason for this? Carbon dioxide is again a polar molecule, so it should possess some dipole moment value, but its dipole moment value is equal to 0. The reason is based on the structure of carbon dioxide molecule. The structure of carbon dioxide molecule is linear in shape. So I am going to draw the carbon dioxide molecule, carbon with double bond O, double bond O. Okay, these are all the Levy structures, but we are not showing the lone pairs here. Okay, now you know that oxygen is highly electronegative. So what will happen? The bond dipole will be in this direction, and here this CO bond, the bond dipole will be in this direction, and you can see the net effect of two bond dipoles. One is in this direction plus the other in opposite direction. They cancel out and the dipole moment value will be 0. So the dipole moment of value of carbon dioxide molecule is 0. What is the reason? Because it is linear in shape, and the two carbon oxygen bond moments are equal and opposite, so they cancel out each other. Okay, now the next example is BeF2, third example, dipole moment in BeF2, beryllium fluoride. Now here also the dipole moment value is 0. So the shape, again based on shape, BeF2 is this. Now BeF2 is again a linear molecule. Then again when you show the bond dipole, fluorine is highly electronegative, so the bond dipole is in this direction, here in this direction. Now what will happen? The resultant dipole moment value will be equal and opposite, so they cancel each other. So the dipole moment value of BeF2 is 0. Now next example is BeH2. BeH2 molecule. Now this is also a polar molecule. All these are polar molecules, carbon dioxide, BeF2, BH2. But still this BH2 has 0 dipole moment. Now again, what is the reason for this? The reason is again the structure is linear in shape. So BeH2, how will you show the structure? BeH2. Now linear in shape. Okay, and two BH bond moments are equal and opposite and hence cancel each other. Now here it will be in this direction and this in this direction. Okay, so that is the third example. Now there is another example, BF3, example number 5. BF3, boron trifluoride. Now boron trifluoride also, the dipole moment value is 0. What is the reason for that? Now here the shape of boron trifluoride is not linear, it is actually trigonal planar, BF3. This is the shape. Now it is said that the dipole moment value is 0. Let's see how it happens. Here fluorine is more electronegative, so the bond dipole is in this direction, this in this direction and this in this direction. Now the resultant of these two bonds will be in this direction and this BF will be in opposite direction. So you can see this plus this, the dipole moment value will be 0. Okay, that is the two equal bond dipoles, the resultant dipole moment of any two BF bond is equal and opposite to the third. So they cancel each other and the dipole moment value will be equal to 0. Now next we have a very important question, that is the dipole moment value of NH3 ammonia, okay, is greater than the dipole moment value of NF3, nitrogen trifluoride. Now I told you, if the electronegativity difference is more, then in that case the dipole moment value should be high. But here it is just the opposite. It is said that the dipole moment value of ammonia is greater than NF3. We know that fluorine is a highly electronegative atom. Okay, but its dipole moment value is less. What is the reason for this? A very important question. The question is the dipole moment value of ammonia is greater than NF3. Give reason. Now the answer is based on the structure of ammonia and NF3. Okay, now in this case there are two dipoles. One is bond dipole. You know what is bond dipole? Bond dipole is the dipole moment due to individual bond. Second is orbital dipole. Orbital dipole, that is the dipole moment due to lone pair of electrons. Okay, now let's see the structure of NH3 and NF3. Both NH3 and NF3 has same structure, that is the shape is pyramidal. Pyramidal in shape. Now I am going to draw the shape of NH3 and NF3. Nitrogen, H3. You know that nitrogen has 5 valence electrons, out of which 3 electrons are used to form bonds, 3 bonds with 3 hydrogen. Now there is a lone pair of electron present on nitrogen, which is present in an orbital. You will learn about the concept. You have already learned the orbital, nitrogen. Okay. Now NF3 also same shape, pyramidal, again with a lone pair. Now let's draw the bond dipoles. Now here, when you compare the electronegativity of hydrogen and nitrogen, you can see that nitrogen is more electronegative than hydrogen. So the bond dipole direction will be like this. Okay, now here we have a lone pair and we have a dipole moment due to lone pair of electron, which is called the orbital dipole, and that will also be in the same direction. Okay, so here the net dipole moment will be in a single direction. Now you look at NF3, fluorine is more electronegative, so we have the bond dipoles in this direction, whereas the orbital dipole will be in opposite direction. So you can see that in NF3, what happens? The bond dipole or dipole moment due to 3NF bond, that resultant dipole moment is cancelled by, it's not completely cancelled, that resultant dipole moment by 3NF bond is cancelled by the orbital dipole. Okay, since it is in opposite direction. So what happens? The value of dipole moment will be smaller than the dipole moment value of ammonia. Okay, so that value is for ammonia, the dipole moment value is, mu value will be 4.9 into 10 raised to minus 30 d by, and here it is 0.80 into 10 raised to minus 30 d by. Okay, so in NF3 the orbital dipole, because of lone pair, that decreases the effect of resultant NF bond moments, which results in low dipole moment value for NF3. Okay, so these are the examples for the dipole moments. Now next let's see fajangs rule. So this polarity of bonds explained how the covalent compounds get a partial ionic character. So next we are going to discuss fajangs rule. That is how an ionic compound gets a covalent character. This is described by fajangs rule. Now the ionic compound possesses some covalent character, which is described by fajangs rule. How is it done? When a cation approaches an anion, the electron cloud of anion is attracted towards the cation and get distorted. This effect is called polarization of anion. Polarization of anion. So this is fajangs rule explanation. Okay, so how will an anion gets polarized? When a cation, positively charged ion, approaches an anion, the electron cloud of anion gets distorted as it is attracted towards the cation. This is called polarization of anion. Now who is doing that polarization? Cation. So the power of cation to polarize anion is called the polarizing power. So cation has the polarizing power because it polarizes the anion, and the tendency of anion to get polarized is called polarizability. Now greater the polarization produced, more is the neutralization of cation by anion or neutralization of charge, and hence ionic character decreases and covalent character increases. So what happens when this cation polarizes the anion? The charges get neutralized, not completely. There is a small neutralization of positive and negative charge in the ionic compound. So what happens? The ionic character decreases and covalent character increases, and it results in building up of electron charge density between the nuclei of both the atoms. Okay, now this is fajangs rule. So how is that done? When a cation approaches an anion, the electron cloud of anion gets attracted towards the cation and it gets distorted, which is called the polarization of anion. And the cation, the power of cation to polarize the anion is called polarizing power, and the tendency of anion to get polarized is called polarizability. Okay, now let's see the factors that favor polarization. Factors. These factors are very important. We have application questions based on these factors. The first factor is smaller the size of cation, small size of cation, and larger the size of anion, large size of anion, greater is the covalent character. Greater is the covalent character. So, if the cation size is small and anion size is large, then greater is the polarizing power of cation on anion and greater is the covalent character. So, this is the first factor. Now, second factor is greater the charge on cation. So, we know that as the charge on cation, positive charge increases, size of the cation decreases and greater will be the covalent character. Okay, so we can say that the polarizing power of cation, the polarizability of anion and the extent of polarization of anion determine the percentage of covalent character in ionic compound. So, the factor is, first factor is size of cation, small size and large size of anion. Increases the covalent character. Now, the second factor is the charge on cation. Greater the charge on cation, more is the covalent character. Now, let's see a few questions based on this polarization or covalent character. First question, lithium chloride is more covalent than potassium chloride. Now, if you take lithium chloride and potassium chloride, the anions are same, they are chlorine. Cation is lithium and potassium and the charge is same, +1, +1. Now, you know that potassium is bigger in size and lithium ion is smaller in size because as we move down the group, size increases. So, lithium is smaller in size. So, we know that as the size of cation decreases, what will happen? The polarizing power of cation increases. So, we can say the polarizing power of lithium ion Li+ is greater than K+ due to small size of Li+. So, these two terms are needed, very important. First is the polarizing power of lithium ion is greater than potassium ion and the second word that is needed is due to its smaller size. Now, the next question is lithium iodide Li is more covalent than lithium bromide. Now, here the lithium iodide and lithium bromide, the cations are same lithium but the anions are different. One is I- and the other is Br-. Now, we know that I- has a bigger size than Br-. So, greater the size of anion, more is the covalent character. So, what will be your answer? I- is larger in size than Br-. So, electron cloud of I- gets easily polarized. So, Li, lithium iodide is more covalent than lithium bromide. Now, the last question here is aluminium chloride is more covalent than magnesium chloride. Why? Now, the answer for this is here aluminium chloride and magnesium chloride. The anions are same but the cations are different. One is aluminium and the other is magnesium ion. Now, aluminium, you know what is the charge? Al3+ and magnesium has charge Mg2+. So, as charge increases, the size of the cation decreases, polarizing power increases. So, your answer, since Al3+ has smaller size compared to Mg2+, Al3+ has high polarizing power. Okay. Now, next we have a question from the back. The question is this: arrange the compounds or the bonds in increasing ionic character, and few ionic compounds are given: lithium fluoride, K2O, N2, SO2, ClF3. You are asked to arrange in increasing order of ionic character. Increasing order of ionic character. Now, increasing order means small to big with less than sign. So, you know that ionic character increases if there is a large electronegativity difference between the atoms. Now, if you look at this, which has the large electronegativity difference, it is lithium fluoride. Lithium is in first group, fluorine 17th group. Very large difference in electronegativity. So, you have to arrange in increasing order means small to big. So, which will have the smallest. N2 is a covalent compound. So, N2 will come first, less than SO2. Sulfur and oxygen, same group they are. So, they show mainly covalent character, less than ClF3. You know, chlorine and fluorine both are halogens. They are called interhalogen compounds, which we will study in class 12. So, after the ClF3 comes K2O, potassium oxide, and finally comes our lithium fluoride. So, this is the order, increasing order of ionic character, which means lithium fluoride is ionic in nature, highly ionic character, and N2, you know, it's a covalent compound. It's formed by sharing of electrons, N2. Okay, so this is the answer. So with this we complete the polarity of bonds and fajangs rule. Thank you.